Between July 2021 and December 2023, 508 autonomous vehicle crashes were reported in the US. This raises the question of how can we ensure these technologies function safely and effectively in real life, where challenging weather conditions may happen all the time. My name is Li Fuzhang, and today I propose to you the perfect solution for the issue, SFTW, which stands for Self-Guided Filter TransWeather Model. This approach is specifically designed to restore weather images by removing noise, recovering lost features, and enhancing clarity. In simple terms, it ensures that what a machine with the model sees is as close as possible to what it will see on a perfect day when it is working under adverse weather conditions. What did I do? I built upon a model called TransWeather, which was introduced in 2022. TransWeather was built on a transformer-based architecture, which performs the best in modeling long-range dependencies in images. This capability allows the model to identify both global and local relationships within an image. Key components include an encoder. The encoder in TransWeather is used in extracting features and representations from the input images. It uses multi-head self-attention system and feed-forward networks, FFN, to model the long-range dependencies and encode features at multiple levels of abstraction. This allowed the model to understand the global context, such as recognizing the patterns in rain streaks or fog dispersions. The decoder works with the encoder by reconstructing the restored image from the encoded features. It uses query, keys, and values (QKV) mechanisms to focus on the important regions of the image, ensuring that the output image retains the structural consistency and the sharpness of the original image. Now, the convolutional projection layer matches the resolution and images of the feature maps between the stages, ensuring smooth information flow. This layer helps align the encoded features with the decoder's requirements, especially for details like edges, textures, and color gradients. Now, a key strength of TransWeather is a single encoder to decoder structure, which allows it to process multiple weather conditions within a single model. Unlike traditional approaches that require a separate model for different types of weathers, this design has optimized the restoration process and also reduced the computational requirements for restoring images in the field. There are some limitations of TransWeather too. For example, its feature extraction is relatively shallow. It has relied on VGD16, which is a shallow backbone, which has limited its ability to extract deep and complex features, which makes it less effective in terms of restoring intricate patterns such as light streaks or raindrop textures. TransWeather was also designed to process static images only, which lacks the ability to handle dynamic real-time data streams, making it unsuitable for applications in real life. So we introduced 3 targeted innovations. The first one is the self-guided filter layer. The self-guided filter layer in SFTW removes noise and preserves the edges and textures, which maintains the structural similarity. Unlike traditional filters, it can dynamically learn and adjust its own filter weights during training, making it highly effective in terms of processing mixed weather effects, where the model should remove noise, balance detail preservation, and degradation removal at the same time. SFTW also replaces the outdated VGD16 with a more advanced ResNet50 backbone. ResNet50 has a deeper architecture, and residual connection can enhance the feature extraction, which is better in terms of high-level features, like light streaks to dense fog, with improved generalization and stability. Third, SFTW introduces real-time video processing, which is the first ever model existing to ever do this. The innovation allows SFTW to process dynamic data streams for applications like autonomous vehicles, AR/VR devices, and surveillance systems, which gives the restored frames with minimal latency and lag for practical cases. So what do we find? Through the rounds of testings, I found that the SFTW model achieves significant advancements in both metrics and real-world performance. Let's look at the quantitative metrics. Using PSNR, which stands for peak signal-to-noise ratio, it measures the effectiveness of noise reduction. The baseline TransWeather achieved 29.52 decibels, while the innovative TransWeather has improved to 29.71 decibels, which is the highest among all the compared models. Similarly, SSIM, which evaluates the structural similarity to the ground truth, it scored 89.62, maintaining one of the highest performing models ever existing. But the numbers cannot fully tell how well the image is restored. Visually, SFTW excels too. In RGB histograms, degraded images shows dullness and low contrast, and SFTW restores the brightness, color vibrancy, and contrast, which is almost perfect to match the ground truth. In HSV, it recovers the natural hues and the color consistency of a more realistic output. When analyzing the textures, we used LBP and edge and corner detection, which clearly shows that SFTW sharpens and defines structural details, recovering the image's edges and boundaries. Most importantly, SFTW is practical. It's the first ever model capable of real-time video restoration, able to process all dynamic environments like rain, fog, and haze at the same time. We can adapt SFTW with other computer vision algorithms, which improves the visual clarity and accuracy of all these systems. We're one step closer to making them more safer and dependable for everybody's everyday use. Thank you.